Um, Hi. Imagine if you want to estimate uncertain variables in real-world application so that autonomous agents could make better decisions under uncertainty. For example, in multi-target tracking, when you have multiple targets and multiple sensors to find the position of those targets, sometimes measurements are noisy, and these measurements can um, actually um, affect each other, can be correlated, can be dependent of each other. Those dependency. So measurements are often noisy and dependent to each other, and that makes this optimization problem or estimation problem very complicated, very challenging. But in reality, most of systems are like that. They are not certain. We always have some tolerance, some noise, and we need to consider that. And also, we have dependency in many systems, especially in multi agents, when they are helping each other or they are competing each other. We always need to consider that. And how we can make this um, type of questions more simpler, and also make it generalize, make it like a systematic way, find a systematic way to solve this category of problems. And that is not all. What if instead of estimating a single random variable, the system can estimate a full behavior of the agents, or like a process role of that actually agent. So instead of having one random variable, we have a set of random variable. We have a random process. We have a function. We have a random function, random process. And that makes it more advanced and more complicated. I have been working in interdependent Bayesian models and random processes for more than 5 years. And today I will explain how interdependent factor graph optimization in artificial intelligence and estimation can help to address this kind of problems. Before going more deep to how use actually the multiple interdependent processes and how we can optimize that, we need to start with some basics. The basic that we need to know is Bayesian approach. What if you need to determine some variables in a simple normal system? We just have one, for example, agent. So that complex problems like, for example, path planning, or target tracking, or even map coloring could be solved efficiently under these constraints. For example, in map coloring, the goal is to find the minimum number of colors required to color these areas, but no two adjacent regions share the same color. In path planning, we want to find the actually path, we want to find the route from a source to destination with maximum safety and a minimum collision. Maximum safety means they be as far as possible to obstacles, and as smooth as possible. And in target tracking, the objective is to estimate the state of the target given all the measurements that can be read by the radar or lidar or sensor or camera. And this is not all. What if we how we can make it a systematic way to do that? How we can make it like a flow chart to just get input and do all this together to make output? In this actually paper, I'm gonna explain that. In this presentation, I can explain that. But let's go a little bit about Bayesian approach. Why this is Bayesian? Bayesian coming from Bayes formula that I'm gonna explain it here a little bit. Okay. Normally, in all of these type of questions, like path planning, like target tracking, or map coloring, because this stochastic is not certain, the environment is not certain. We have uncertainty. So in this case, we can't find exact value of x. We cannot find exact value of x. We can find just the estimation of that x. We can find so the optimized value for x. Oh, let's call that theta actually to be, for example, a trajectory. Okay, so imagine we have a theta, and this theta is the trajectory that's supposed to be like we have lots of obstacles here, and we want to find this trajectory, and we call it theta. But how we can find this trajectory? We cannot find exact trajectory, but we can find actually the probability of this. We can find this probability of this actually path given all the events that happening. And when we actually maximize this or argmax of this, give us theta. So this is the main formula that we need to use for this family of problems to find theta, because finding this probability is possible, because probability of theta given all the events, that is all events or all constraints, is based on Bayes formula. You can break this down. You can break this down to P of theta multiplied by P of E given theta, divide by P of E, because P of E is a constant. It's not effect on optimization problem. We can take that out. This is called actually prior. This is prior information. Like a start point, end point, they are prior information. We know this information. And P of E given theta is a likelihood of those events. We have multiple events, like for example, events of being as smooth as possible, events of being far as possible as obstacles, you know, these kind of events. Okay, so this is Bayesian method. So I just wanted to explain how Bayesian method works. So in Bayesian method, again, we find a posterior, this is called posterior density. Posterior density of theta given all the events. You just need to maximize this probability and find theta that maximize this. So that's something that we want to do in this actually presentation. But how factor graph related to that? Factor graph is a bipartite graph. actually factor graph representing Bayesian formula. How? With so in factor graph, imagine you have this trajectory. First of all, this trajectory is a continuous function. We need to make it, a vector value function, or wave points for that function. So this, imagine we put 10 points to summarize this trajectory. Instead of having this function, we have a vector representing that function. This vector called vector value function or wave points. Okay? Wave points. So wave points or vector value function is these functions. So they also are a state of the trajectory. In a state of the trajectory is something that we want to optimize. Is a theta. For example, theta 0, theta 1, and theta n minus 1. If you have n, actually a state to summarize this. Another thing, so we have, this is a state is something that we want to actually optimize. And also we have another things, and that is those events or those factors. Those factors is the likelihood of that event. Like for example, here we have a start point. Factors, mostly for a state we use empty circle. For events or for factors, we use another shape like rectangle, circle again, but the field color, you fill it with color. So endpoint, a start point, a smoothness. A smoothness is between them, between two states. This is a smoothness. We use, for example, a square for that, or rectangle. And another one is obstacle avoidance. Obstacle avoidance is another factor. For example, we use a triangle, for example, field triangle. All of them have this factor as well. So it's showing closest obstacle to that state. For example, in this case, the closest obstacle is this one, and the distance to that can consider as a cost, and so forth. So as you can see, this creates a structure. I need to explain about in Bayesian approach. Normally, two graphical model can be used for summarizing a Bayesian problem. One is BaseNet or Bayesian network. That Bayesian network is a little not flexible, and the other one is factor graph that you can see here. So factor graph is more flexible and is a bipartite graph. As you can see in this graph, the nodes, we have two types of nodes. Some nodes are called a state, that are the values that we want to estimate, and some nodes are consider factors. Okay, some consider factors like a smoothness factor, like obstacle avoidance, like this triangle is obstacle avoidance, and this is a smoothness factor. Okay, and that's a start point and end point. We can explain that in next slide. So is bipartite undirected graph, and is very flexible for when you have many constraints, for some problems that involving multiple different constraints and satisfactory conditions. um, they are very good. Like these factor graphs are very useful in these cases. And also when yes, um, the reason that factor graph is very useful in this case, because the factor graph is more structured and um, um, interpretable. You can interpret it, you can understand it, you can see the structure. As you can see in this factor graph, you also can see the path is more, tangible, and um, uh, you can interpret it, you can explain it. It's more explainable. That's why factor graph is so important in so many applications these days, because it's explainable. You can explain it and mathematically prove it. It's something like that. Okay, so that's called constraint factor graphs. Constraint factor graph. Okay, let's go see for one example for path planning, because path planning is one of the important actually questions that we have. We want to see how path planning works. In path planning, we have a start point and end point, and we have an environment, like two-dimensional environment, and this environment has some obstacles, like some rocks, some roads, some buildings, and the question is to find a trajectory from source to destination that actually is as short as possible and also as smooth as possible and as safe as possible. This is the road. As safe as possible means not go too close to obstacles, something like that. This is the problem that we want to solve in path planning. So everything is uncertain. There is no certain values because robot has some noise and is not certain. Environment is not, and so many uncertainty exists in this environment. First step to solve this problem is to define variables. So define variables because these variables are random variables, and we want to find these variables. The variables in this example, in this path planning, we call it theta, and theta is set of all these points that we call them wave points. Set of wave points, we call them like theta 0, theta 1 to theta n minus 1 for n wave points. For n wave points, or for n vector value function, we have this, and each theta I is by itself is x and y and x dot and y dot. Okay, again, this is for a holonomic robot. Holonomic robot is the type of robot that can move in any direction, like a drone can go in any direction. But non-holonomic robot, holonomic robot. In non-holonomic robot is a car-shaped robot. Car-shaped robot, non-holonomic, non-holonomic robot has angle too, theta. Not theta, we use theta, like alpha, for example. This is non-holonomic. Most of the robots are right now are non-holonomic. For non-holonomic, this state need to add theta as well. But in this example, we are consider the simple case. We don't consider non-holonomic robot. This is just holonomic for now. For non-holonomic robot, we have more constraints. We can explain that in another session. Okay, so that's the state that we need. We need to find this state in each step. This is something that we want. This is the objection. This is the objective value that we want to find. The state of the this trajectory. And this trajectory is a set of random variables. That's why it's a process. We are finding this process. Sometimes it's called actually process role, because it's the behavior of this agent, process role. Okay, but what kind of constraint we have? We have normally three types of constraints in this path planning example: prior information, prior factor, a smoothness factor, and obstacle avoidance factor. Okay, we can explain each one separately, but before that, I need to explain a little bit about constraints. As we explained in the previous slide, the problem that we want to solve is actually x star. X star means the optimal value, theta star, the optimal value of the trajectory. The optimal value of trajectory is actually arc max of posterior density of theta, given all the events that have happening. So in this case, and that can break down to actually arc max of p of theta, p of e given theta. P of theta is a prior information, and P of E of theta is constraints. And that means probability of that constraints given that trajectory. Okay, these constraints, this is also called likelihood of the event. This is also likelihood of the event. So in these factors, we want to find this. We want to find probability of, for example, being in a first point. Okay, so for example, probability of events given theta. We want to find this probability. The best likelihood function that can be used in artificial intelligence is exponential family function. I will explain why, but exponential family function, like Gaussian shape, that is bell shape, has negative 1 over 2 cost of that event. Okay, so this is the likelihood of the event. This is also called general form of constraints likelihood. General form of constraint likelihood is this, and this C is cost of that event. Cost of that event. Okay, why we use this likelihood? The reason is because of the bell shape. For if we have cost, and this is P of E given theta, and cost of E theta. If we draw this function, because it's Gaussian, is like that, bell shape. It means when the cost getting smaller and smaller, the likelihood of that event getting higher and higher. And that's the reason. Another reason for exponential family is or optimization that makes optimization very simple to solve, and also converge, make the converge. Okay, so so this is the general form for constraints. So this is important. This is general form for all constraints. Okay, good. Now let's go for check for prior smoothness and obstacle avoidance to see how we can do those things. So if the function is like that, the only part that we need to compute is this cost. What is this cost? Let's find this cost for each of these. Let I clean up this. Okay, so first is a start point and end point. So cost of, let's choose another color, maybe blue. Okay, cost for being in a start point for theta 0, because it's just for theta 0, for theta 0. If the theta 0 is close, because a start point is given, so the cost is the distance between theta 0 and the start point. And this distance is normal distance. We sometimes call it norm 2, and it has a covariance. So this also called Mahal distance, sometimes Mahal distance. And mathematically, so for example, x to sigma is equal to x transpose sigma reverse and x. So this is the formula for this. It's like normalized by this sigma, and this sigma is a covariance matrix. The covariance matrix is actually diagonal matrix. The sigma is a diagonal matrix, like in this case is 4 by 4, sigma 2 of x, sigma 2 of y, sigma 2 of x dot, and sigma 2 of y dot, and the rest are 0. This is how we can do that. And in a start point and end point, these sigmas, these tolerance, these variances are very small, because we want to be exactly there. Okay, it's very small. Okay, so this is the cost of being in a start point. For end point is also the same. Okay, let I clean here now. Let's go for a smoothness. A smoothness is also very important. So in a smoothness, we need to have a dynamic of movements. We need to have dynamic movement, but so this is a start point, end point. A smoothness is between, let's make it between two states. I remove these states and makes them for that. Okay, and another one here. This is a smoothness factors. So the cost for a smoothness for theta I, because it's between theta I, like theta I and theta I plus 1. Between theta I and theta I plus 1 is actually can be computed again the same way. So is actually if the transition matrix or transition function for theta I minus theta I plus 1 is this is for start point. This is for smoothness. So again, distance. Again, this is normal distance. This is mahal distance between transition function of theta I, because we want to see if we give the transition to this, how this gonna be close to that. Transition is showing, for example, if it's constant velocity, you just need to multiple velocity by time to add to previous theta to find a new theta. It's coming based off the dynamic of the model. When you digitize it, it's gonna be a matrix that you can multiply by the theta I to find theta I plus 1. So we want to see how these two are close. Transition. This is transition function. Transition function, as I explained, coming from the dynamic model. We can talk about the details later. I just wanted to show you the function. For obstacle also we have function. Let I clean this to make some space. Okay. For cost of obstacles, cost of obstacles is for all of them. Cost of a start point is 1. Cost of end point is 1. Cost of a smoothness, because it's between them, is n minus 1. If the number of states is n, the number of a smoothness factor is n minus 1. And cost of obstacle is n, because for all of them you have. For this you have, consider this triangle. For this one is also that. For this is this. For this is, for example, here. For this state is like there. For this one is here. So as you can see, for each state we have this factor. So the number of factor is for all of them. So it's for all of the theta. And the cost is again, the cost is again normal distance. This is normal distance. Sigma obstacles. But in this distance is a sine distance field. Sine distance field of theta. Sine distance field is a function in like image processing. You can use sine distance field to give you the minimum sine distance field. I'm gonna explain it here. Sine distance field. Sine distance field give minimum distance to obstacles. Minimum distance to obstacles. Like for example here, the minimum distance, the minimum obstacle is this one, so it's considered this distance. For here, the minimum distance to obstacles is this one, not this one. You know, that's how we can compare. It's easily in. It's just a function. You can use it in Python. So sine distance field is actually can compute the cost of obstacles. So it means how much you are close to the obstacles, to the closest obstacles, you know. That's why we consider that sine distance field. So this easy can be computed. So that's it. So we have these factors. We have these factors, and then I clean this here to put other parts. And then the next step is to formulate the joint probability. And we already did. This is the joint probability that we already explained it here. So it means this joint probability can be written as this. So it's going to be equal to R max P of theta like P of theta 0 that we have it here. P of theta n minus 1, P of product for n minus 1, P of maybe P of a start point, P of end point, P of actually a smoothness, theta I plus 1, and the product for n, P of obstacles, theta. As you can see, this is all product. They are all multiplication. So so if we find this, we can find theta star. We just need to solve this optimization problem. But this optimization problem, we can do a trick. The trick is, if you have optimization problem, we always can get logarithm. Logarithm is not change the trend of optimization. So you always can get logarithm. If you get negate of log, this maximization gonna get minimization. So that new, after getting log, this theta star gonna be equal to arc mean. It's gonna change to mean for theta, and this gonna get summation. And because, as you can see here, exponential gonna remove after getting log, and the cost gonna come up, and it's gonna be very interesting. So so we bring minus 1 over 2 out, and the rest is just cost of start point plus cost of end point plus cost of, oh, here we have summation n minus 1 cost of smoothness plus cost of obstacles. And look at how easy this can be. This is just, and look at all of these costs. They are all actually a square. They are just a square. So these problems becomes a least square problem. So this is a least square problem, or sum of least square problem. Sum of least square problem. That complex problem can get easy to the least square problem, and least square problem is very well known. You can solve least square problems with very different methods, including Gaussian-Newton methods. That is very simple method. And so this gonna break down to a simple iterative method like Gaussian-Newton is very simple method. You can implement it for this because everything is Gaussian in here. Everything like is exponential family. This can get converged for sure. So convergence is secure. So you always can get converged. So Gaussian-Newton works very easy in this case without any problem. To explain about Gaussian-Newton, let I clean up here a little bit. So this is the problem that we want to solve. I remove the rest. Okay, let's see, a little slow. Okay, so what we want to find here is like this. In Gaussian-Newton method, you need to make a J matrix. A J matrix is Jacobian, because how Gaussian-Newton works is like, because it's minimization. You need to find the derivative of cost. You need to find the derivative of the cost and try to move in the direction that makes it minimize. So because derivative always showing the direction of movements of that function, showing, because derivative, for example, if the function is like this, the derivative is showing the direction of increasing or direction of decreasing. So that's why we need to have this derivative. So we call it J matrix, derivative or Jacobian. So this is the matrix. Each line is for one factor. Each line is for one factor, like a start point factor, and it's just for one. The rest is zero. For a smoothness factor, we have n minus 1. A smoothness is for two states, and this is for states. These columns are states, rows are factors. This is for 2, this is for the next 2, and go to head to, because it's for 2, because it's between two states. So this is the Jacobian for that, and computing derivative here is simple. Derivative is, for example, here you can find the derivative is 1, for example, or whatever. Derivative of this is also very easy to compute. Derivative of sign distance field also given. You can there is a function for that. We have that in our code as well. You can see that later. So this is for a smoothness. For end point, you have another one. These blocks are 4 by 4 blocks. Okay, because the state is actually 4. The dimension is 4. Okay, and the rest is we have a start point, end point, and the rest is for a for collision avoidance, obstacles avoidance. Obstacles. For obstacle avoidance is all for a state. The rest are 0. We just have 1 for a state, but this is not 4 by 4. This is a block of 1 by 4. This is like 1 by 4. Because for we don't need to change all all of these points. We just need to it's a scalar, because for obstacles it's a scalar. That's the reason. And that's the J matrix. We also can compute the cost matrix or cost vector. We have also cost vector. For each factor. For a smoothness, we have one value. For a start point, for a smoothness, we have multiple value. For end points and for obstacles, we have this vector too. So we have cost, we have J, we also have a sigma. This big sigma, because as you see, we have these covariance. If you put them in a actually diagonal shape, this is for a start point. This is for actually a smoothness. This is for a smoothness, and this is for endpoint, for example, and this is for that obstacle avoidance. We have this sigma 2. We use Gaussian-Newton saying that the answer for this, if you have J matrix, if you have C vector, and if you have sigma vector, you can compute delta t, delta theta. You can find the change of theta. how you can find change of theta. So let I remove this part. We can make a space. Okay, so based off Gaussian-Newton, Gaussian-Newton actually making this formula, J transpose sigma minus 1 J delta theta is equal to actually J transpose sigma C. Okay, so sigma is given minus 1, sorry. Sigma inverse is given. Sigma inverse, because this is a triangular matrix, or diagonal matrix, computing this sigma inverse is easy because you just need to inverse each block. And the cost is given is easy because you can just compute that. The J is also easy because the gradient matrix is also easy to compute. So we have all parts in this, and we can find delta theta. And if you have delta theta, we can have theta k plus 1 is equal to theta k plus delta theta. That's it. So if we repeat it multiple times in an iterative way, when it start converging, after multiple time you have the new theta. So this is how this method works. In this method, because we just considered one robot or one agent, we don't have interdependent factors. We just have normal factors. But in next slide, we're gonna see how interdependent factors also can affect in that.